Hi everybody, in this example we would like to calculate some values. First of all, we would like to know the reactional torque TA and TB in this case. And secondly, we would like to know shear stress AC, shear stress which is acting in this part AC and CB. And finally, what's change of rotation at this point C. That's our question. At first, let's think about the problem generally. We have some shape which is attached to mounted A point and B point, which is built in the wall. And left side, small diameter dA, and right side we have diameter dB. In the middle of this component, we have torque T0 is acting like this one. Some characteristics related to the segment or component is given like this one. The length on the left part is LA, and the right part is LB. And when we add both of them, then total length is L. This is given. And we have polar moment of inertia. On the left side, this segment, this component is IPA. On the right side, we have IPB. That's polar moment of inertia on the right side. Okay, that's generally given to this equation, question. We would like to know TA, torque which is acting, reactional torque TA and TB. We would like to know that. In order to find, we must think about some compatibility relationship. When we isolate on the right side part, then component can be like this one. When T0 is acting like this one, something is changed at this point B, due to torque T0. And when you draw free body diagram, the reactional torque TB is acting like this one. By TB, you can imagine rotation of angle can be happen. The rotation of angle is phi 2. And we would like to calculate finally, firstly, TA and TB. And now let's think about step by step. When you consider this figure, then we have this direction is positive. Then we can say TA, torque TA, plus T0 and minus TB equals 0. This kind of equation is available because torques are in the state of equilibrium. And next, we introduce geometrical compatibility. Geometrical compatibility. What does that mean? Geometrically, it should be like that. We thought about here by torque T0, we thought phi 1 is happening like this one. And another imaginary reactional torque is like this one, then phi 2 happens this one. But eventually, when you consider this point, at this point, phi 1 plus phi 2 equals 0. Actually, at this point, at B point, nothing was happened because, on the right side is fully fixed to the wall. Then the rotation of angle cannot be changed. That's the geometrical compatibility. by this formula, we can calculate the phi 1 equals G I P T L. This kind of general relationship. Then we introduce on the left side, we assume G, shear modulus of elasticity is the same, we assume. Then IPA on the left side, IPA, and T0, phi 1, and you think about just this amount of one, this length, LA is acting here. Then change of angle is like that. And phi 2 is what? Phi 2 is what? Plus phi 2, when you consider this one, it's slightly different. When you consider that one, phi 2 is, this torque is acting here and here at the same time. Here and here at the same time. We must consider that. Firstly, due to TB, G, I, P, A. On the left side, length is LA, and which is acting here, TB. On the right part, this one is also elastic, and we can introduce G. Let's assume shear modulus of elasticity is the same, and I, P, B, right side is different, and L, distance length is B, and acting one is TB. Okay. And the whole value is 0. Okay, left side is phi 1 and phi 2 is 0. Then based on two equations, first one is this one and second one is this one, then we have two unknowns, TA and TB, Then finally we can find TA and TB by solving both equations. Then first one, number one was cleared. Okay, let's move on to next example. Next question is shear stress tau large AC. This one is what we can apply IPA TR. Let's say TA. We apply left side TA. Radius is TA over 2. This one is tau AC. Okay, on the left side, when we assume, then this length in this AC segment AC, we assume TA torque is applying. Then tau AC we can calculate, and tau CB also is IPB TB, and diameter dB over 2. This value is tau CB. Of course, this one is shear stress. That's why Newton per meter squared of unit we can consider. That's all. And finally, we calculate number 2. And finally, we would like to calculate phi C. Phi C is G, I, P, and torque T and L. And on the left side, when you consider IPA and TA and length LA. When you introduce this one, we already know TA and not L, sorry, this one is A, LA. All the values we know that. Finally, we have phi C, change of rotation, which is written in radian value, Okay, in this figure, in this example, we introduced geometrical compatibility like this one. Geometrical compatibility. It plays very important role to solve or to get another extra equations. Firstly, we would like to know TA and TB, and we introduced equilibrium of torque. Then we can derive this equation. And the next, geometrical compatibility, based on geometrical compatibility, we have this kind of relationship. At this point, right side, at this point, B point, the movement or change is zero. When you apply this kind of equation, then when we substitute the basic relationship between them, then we have this kind of equation. Then finally we can find TA and the TB torque. Next, we would like to know shear stress, which is acting left segment and the right segment. Okay, left segment, right segment. Key point is to introduce TA and TB. And finally, we would like to know change of rotational deformation at point C. And when you consider left side, just then we can say like this one. That's the solution for example 3.9. In this example, we consider a cantilever bar. This one is actually cantilever bar. The bar has just one solid circular cross section, which has solid circular cross section bar, which is built in, which is attached firmly on the left side to the wall A. And we have three different kind of condition. The first one, we have TA is acting on the right side, point B. And next one, we have here, torque is acting in the middle of the bar. Third one is here. First one is there. TA is on the right side, and TB. Two torque is acting at the same time. We have three different kind of combination. A on the right side, and B we have in the middle, and C we have two different places. And our final goal is to find the strain energy for each case respectively. To find the strain energy is our goal. Of course, we have some data related to TA, TB, and shear modulus of elasticity is 80 gigapascal. And polar moment of inertia for this material is given this one. Be aware of the unit. Okay, we would like to know strain energy, which is stored in each case. Actually, strain energy can be calculated like this one. In the case of torsion, Gi, polar moment of inertia, T squared L. This one is strain energy. let's say this one is U. You can derive like this one. When you consider tension and compression's case is slightly different. In that case, we thought about two EA P squared L. This one was stored energy in the case of tension and compression. We have some similarity between torsion and tension and compression. The shape is very similar, very similar. Instead of GIP, we have EA. Instead of torque, we introduced here force. When you consider strain energy, final unit is Newton meter. That means joule. We have the unit joule because it's energy. Energy is defined by joule. When you substitute all the details like this one, final unit is joule. Joule is actually Newton meter. Okay, that's basic background for this case. And another basic one is like this one. When you draw a graph between torque T and change of angle, rotational change, we can introduce some kind of linear relationship. Because phi equals GIP TL. LGIP is constant. That's why there is some kind of T equals K stiffness K T then phi. We have this kind of linear relationship between change of rotation and torque. Then it's a kind of spring. It's a kind of rotational spring. Between torque and rotational angle we have some linear relationship like this one. Okay, then strain energy is what? When you consider this triangle's area, this one is what? Expressed T phi over 2. This area is what? Actually strain energy, which is stored during rotational change, rotational deformation. Okay, that's the background for strain energy. Anyway, in this case, our goal is to find stored strain energy for each case. The first one, let's say UA equals G to GIP, polar moment of inertia, TA squared L, because we can consider just L is homogeneous and the same cross-sectional area. Of course, IP polar moment of inertia is you can, if you like, IP equals 32 phi d. You can do like this one. Okay, next one. In this case, UB. Let's say UB. This one is what? TB is acting in the middle. That's why change of component happens just in this length. On the right side, nothing happens. It's free from the rotation. Then we can say GIP and TB. This one is TB squared. And length is L over 2. That's the second case. The final case, let's say UC equals. We should consider left side and right side at the same time. When you consider left side, when you consider this side, TA and TB, torque TA and TB is acting on the left side. And right side here is acting just TA. TA is acting just right side. Okay, then we first think about on the right side, G, IP, and TA squared length is L over 2. That's for right side. And when you consider left side, plus G, IP, and length is L. And acting torque is TA plus TB squared length is L over 2. This one is stored strain energy. Okay, we've calculate UA and UB and UC. And we have this kind of one, and we can calculate UA. UA may let's think of this one. UB is 2G 80 gigapascal. This one is G, IP is multiplied 79 point etc. exponential 3. And when you introduce TB is 150 Newton meter, and length L is let's say 1.6 meter. 1.6 meter. Okay, then finally you can find UB. UB is written in Joule, expressed in Joule. Okay, when you substitute real value, be careful about the unit. We have different dimension. When you see here, millimeter, gigapascal. Okay, then finally you can have different kind of final answer. And when we've just introduced here this one is what? Polar moment of inertia, but it should be considered and expressed in millimeter. Then the unit must be unified to change to in meters, Okay, then you can finally have good correct answer for this case. Okay, that's for finding strain energy. For